So just a real quick announcement before is that we will have, as usual, our lunch will be afterwards over in the Swanson room. And then after that, starting at around 1:30, 1:45, there'll be time for students to sit down and chat with the speaker some. But with that, let me go ahead and introduce our speaker today, who is Ishrat Dollan. So Ishrat comes to us all the way from Stony Brook University, where she just joined earlier this summer my research group and is going to be working on a variety of topics. But today she's going to actually use this opportunity to discuss a little bit of the work that she's been doing towards the end of her PhD thesis in her seminar. So just a little bit more about Ishrat. So Ishrat finished her Bachelor's of Science in Water Resource Engineering in the Department of Water Resources at Bangladesh University of Engineering. After graduating with her BS, she actually spent a little bit of time working directly with the Institute of Water Modeling, which is part of the Bangladesh government, and focused in that work as a junior engineer. But then, fortunately for us, she decided to come to the United States to continue her education. And so she recently received a master's and a PhD in water resource engineering in the Department of Civil, Environmental, and Infrastructure Engineering at George Mason University, so just down outside of DC. She finished her master's in 2020 and finished her PhD just this year. Prior to joining Stony Brook. I always try to find one interesting thing about a speaker to highlight, and oftentimes I look down far on the resume of the things that aren't at the top. And so one nice thing about Ishrat is that during her time as a graduate student at George Mason, she actually received an award for the best teaching assistant of the year, which I think is impressive for a graduate student. So I'm sure we'll see some of that on display with her presentation today, no pressure. But with that, I'm going to turn it over to Ishrat. Just as a quick reminder, she's going to talk a little bit about trends in extreme precipitation, identifying historical and projected patterns using multi-source precipitation data sets. So I will turn it over to you.
Thank you so much, Dr. Reed, for a wonderful introduction of me. I think I don't need to cover my introduction slide. Thanks all for joining. Good afternoon. So I'll be talking a little bit about my dissertation. I graduated from George Mason in spring of 2023. So there'll be a lot of discussion about that, and later, basically, I'll focus more on my current research at Stony Brook. There'll be a little bit about that. So moving forward, I'd just like to highlight two things basically. Just like during my graduate studies, I actually got an opportunity to work with the National Water Center during a summer of 2019. It was like an intensive program, but it was amazing. You get to meet a lot of people working on water-related issues. Another one is basically last year I was in Millbrook from doing some soil moisture capping, and that's not part of my research. That was like interesting. That's a great opportunity from NASA. So just to give an idea about this, since I'm working on extremes, so definitely that there comes this hydroclimatic extremes. So in general, as you've known, that the high temperatures causing atmosphere to hold more moisture, which is potentially basically to lead more intense rainfall in parts of the world. And research has been shown that the occurrence of hydroclimatic extremes are increasing in different parts of the world. Some of them are like floods, droughts, and heat waves. And what about that? And this one is basically a consensus about the increasing temperature warming from different institutions, and it's more over like a decade, starting from 1880, and it's showing increasing trend. So in general, there is more risk of like more extreme weather events that's coming in the near future. So that's why I'm interested to looking into precipitation change in terms of extreme from basically looking into the past and what's going to be the future of precipitation. And I'm interested more basically the upper extreme or like the wet extremes because like the intensity and frequency of these wet extremes are increasing over parts of the world, and there'll be like more intense hydroclimatic regime throughout the century. And if we look over this map, these are basically stations, the ground stations, and this is from Intergovernmental Panel on Climate Change Assessment Report 6 that shows that most areas over the at a global scale, we see more like higher positive trends compared to the negative trends of like drying or precipitation. And these are like kind of broken down in different continents, and you will see that the precipitation, mostly like looking at the daily precipitation, maximum daily precipitation, and how they are changing at a global scale. So in general, we can say that more areas with a significant shift toward wetter conditions compared to a significant shift toward drier conditions. So, but I look over to different regions and then also look over to the continental scale. So why do we need regional studies? Because there might be like there might be like regional variation in the direction and strength of changes. So what I mean by that direction means like the change of precipitation that can be like increasing or decreasing, and the strength means like the intensity or the magnitude. And also different rates of temporal changes in the precipitation distribution might occur. And these are important to know because it's critical for regional climate assessment and water management. So for example, if an area is like water stressed, already water stressed area, so if we know about this different regional variation and also different rates of change in those already water stressed area, we might be planning for future in a better way. So looking at this map from IPCC, that's like this climate average, and also looking at like climate extremes, I just like have a circle here. This is like Northeast US that shows that it's kind of like from drier to no change zone, but in the same climate extreme, it's more like wetter. So just to give an idea what might be the case in average and the extreme in general. So what I am looking at just two different continents basically. So one of my study will be focusing on more like Northern Virginia or like the DC area, and then I expanded to more Kona scale, contiguous United States. Another one is I'm like shifting my gear to a new study area that's like the high mountain Asia. That's very challenging area to look at the change of precipitation, because you can see this is like the Everest is basically here. Like there's a very heterogeneous terrain, topography there, so many different climate regimes. So moving forward, so I will be presenting some of my results in two aspects. One is like looking at this long-term changes in extremes. I just explained that I'm looking over Konas and also like the high mountain Asia. So in general, if you look at this map, it shows the map of two Americas, which is meant by the one part and one soak. So we see like mostly like the northeast part is like very wet, and if we're going towards the drier part like the west, or like if you look at California, this part is like it's been experiencing prolonged drought for more than 2 decades. Another study area is basically so it's called the third pole because it's interesting because the largest ice mass is sitting here other than the two poles. So it's also called Asia's water tower because it conserves all the fresh water, there are many water tributaries, and we're talking about this is basically Nepal, and this is where this area is basically where the Everest is. Some parts of Pakistan, India, parts of Tibet, and parts of China. So in general, there like the recent study has been showing that the precipitation extremes are increasing over this area. Another one will be like a high impact based analysis that I want to show some results from. I'm looking at Pakistan flood event that happened basically last year during the month of summer. So it's from June to July, June to August is basically my time frame. And you can see the flooded areas over here. It's like, so this is like a tributary, actually, Sindh River, and you can see that like how they're like flooded. And this is coming from Google Earth Engine map, basically. And so moving towards the first case here. So first, I wanted to know what is the precipitation change over the southern mid-Atlantic region with a focus to DC area or the Northern Virginia. So, and I'm using as an analysis product, which is called the North American Land Data Simulation version 2, which is 12 kilometer spatial and hourly resolution. And I'm looking over 40 years period from 1980 to 2018. This was a collaboration among Mason scientists, Northern Virginia Regional Commission, and American Geophysical Union's Thriving Arctic Exchange. So the project objective was to look at the regional vulnerability of flooding in Northern Virginia. So we wanted to know how the precipitation, mostly the extremes, so are changing in this past 40 years. So some of the results are kind of like highlighted here. So if you look at this is basically my study domain. So this is the part of Northern Virginia, this is DC, some parts of Maryland. Mostly I'm looking over this part. So I'm looking at this annual precipitation from 1980 to 2018 from this analogous data. This is like aerial average, like the domain average annual precipitation. So I looked at from 1980 to 2018. In general, if we look at this trend line, it says an upward trend or increasing trend. And this is coming from a linear fitting of this data sets. However, if you see some of the data sets are outside these 95 confidence bounds. In general, there is like kind of from the data sets, there's 16% increase at 4.3 millimeter per year, but this is not statistically significant. So I was like more interested to look at this type of change over each pixel of the domain, like what we see. So we see a distribution.
Could you tell us what the resolution of the?
That's 12 kilometers.
Okay, thank you.
So and one thing I didn't mention. So this is hourly data set. So I aggregated it to daily scale. So if you look at the trends, this is coming from Tilson trend. This is like more up wetting, or the bluish like the more wetting. So these trends are also if you see these areas like northeast part is more having more upward like wetting pattern, and also statistically significant. And I did this significance test only for 3 different significant tests, like from 0.01 to 0.1. And only the markers showing only the significant ones over this area. So there are some negative trends in the southwest part. One thing to remember is basically this part is kind of part of this inflation mountain trail, this part that falls within that trail. So in general, one interesting result from this analysis is like around 34% of the domain it's kind of like is varying from +3 to +5, like it's like above +3 or like 3 millimeter per year it's increasing. And these values are statistically significant at 0.1 significance level. So then I looked at into the seasonal patterns using the same data set. The seasons going from spring, summer, fall, and winter. Spring is combined from March to May. Summer is from June to August. Fall is like September to November, and December to February is basically the winter. So if we look at the plots, if you can see the same, so I'm only showing the significant ones here, three different significance levels. The summer precipitation is increasing over the northeast part of the domain. There are some increase, or also like statistically significant trends over this part in fall, but in general, summer, like these are markedly lower value than the summer precipitation over this domain. Then I looked into one extreme case, which is the daily maximum precipitation. If so, this map, the left one is basically the average of 40 years. So all the 40 years daily maximum precipitation, and the distribution looks like this is the Appalachian Trail this is the mountain range, and the maximum daily precipitation, we see higher values here, about like 70 millimeter for daily maximum. And looking at the trends, we see most of the regions are kind of just like having positive change or like wetting change, wetting pattern in terms of trends. And in general, like 75%, approximately 75% of the area represents a significant trend, and also the significant level is like 0.05. Another interesting thing is to see how this top 5% is contributing to the total precipitation. So this is kind of a ratio. So the top 5% precipitation in each year and how they're contributing to the annual precipitation. The left map is basically just the average, like this 40 years average. And you see this is the more than 50% contribution is coming to the total precipitation over this area, over this over the southeast part. Mostly this is kind of this gradient. However, if you look at this trend, like majority of the region, we see like, okay, it's coming from this top 5% precipitation and they're increasing, and most of them are statistically significant, even at 0.1 level. That's kind of like 99% confidence interval. Then I also looked at this number of extremes. So how I define this number of extremes. So I have a climatological threshold, like 95th or 99th percentile coming from the historical 40 years data. And each year I for producing this map, each year I find the exceedance. So how many times this number of daily precipitation exceeded this 95th percentile, and do the same for 99% of the top 1%. So this is just a linear regression. It shows that in addition, like in top 5%, there will be like 6 additional precipitation at the end of 2018, and for top 1%, that's like 99 percentile, that there will be like almost like a 1% increase at the end of 2018. That depends on my 40 years time frame. So in a nutshell, if we have to combine all this analysis, I also looked at other properties like daily maximum 5 days precipitation in this analysis, but I'm just showing a few bunch of the results here. But to combine, so we see like strong signals in the northeast part of the domain. So mostly like the Northern Virginia, the counties of Northern Virginia at annual average, and some southwest topographic gradient were associated more with the extremes, like the daily maximum precipitation. They're like more if the precipitation kind of like the increased summer precipitation, summer has been contributing more, and if we're looking at this number of daily extremes, like just the basic just exceeding this threshold, we see these extremes are becoming more frequent. So we are seeing that more contribution is coming from this top 5%. And there's in general like severity of the daily extreme precipitation and their contribution to regenerate potatoes are growing in a nutshell. So we have published this paper last year in Frontiers in Climate. If you're interested, you can look at it. So now I'm shifting to greater area, just expanding these to a continental scale, I would say, just not the whole US, like contiguous United States. So what I want to see is like, okay, what should be the projected extreme precipitation here over corners? And for this, I'm using a climate model simulations. That's I'm going to explain in the later slide. But in general, 2 types of questions I was interested to look at, like how will the precipitation will change over this contiguous United States by the end of 21st century, using a new scenario matrix architecture, shared socioeconomic factor 370, and what are the uncertainties associated in detecting these trends at the different national climate assessment regions. So just to give an idea about the data sets and how I did the analysis, is basically I'm using community or system model version 2. It has large ensembles. Actually, it has more than 70, but during the time 70 ensemble members were available, so I used 70. It has 100 kilometer very coarse resolution, and it has like daily temporal resolution. And I'm using only one scenario because that's the available one coming with this large ensemble. So if you look at different NCA region, this National Climate Assessment regions, so I am just giving an example for each grade here. This is, for example, so all of these steps are basically as done for all the grids here. So first, separate, for example, I have two extreme indices. One is like the seasonal total, another is like the daily maximum precipitation, and these are in millimeter scale. I extracted these time series for two different periods from 2015 to 21st century. This is for the future precipitation because the model actually gives the data from 2015 more than 21st, but I actually combined this only for 21st. And then I have a historical part from 1950 to 2014. That's important to normalize my trend results. That's why I did that. So for each index, I extract this time series. I have different quantiles of this distribution. So this is an interesting plot. For example, these are all the circle represents all these 70 ensemble members coming from these individual extreme indices. And the one, for example, I'm looking at only the 95th quantile. So from this distribution, I take the 95th quantile for each year. So for each year, I do this 95th quantile, and then I just feed a trend line. That's basically the field trend line. So, and this has been done for all the pixels here. So just to give an idea for one of the results, it's like the projected seasonal patterns. These are like seasonal total precipitation. Some of the results to highlight from this analysis is basically I'm looking at different seasons. So the column represents different seasons, and the row represents different quantiles. So for spring, if I look at, so some of the results I'm just highlighting here, from this model, I see a drying pattern over southern Great Plains and also Southwest. From the lower quantiles, and if you go to the higher quantiles, you see the similar pattern. And we see a kind of like intensified or like waving pattern in the Northeast, Midwest, and Southeast part. If we go to summer, we see like kind of like a drying pattern in Midwest, and it goes basically, it's the similar pattern you can see across all the quantiles. For fall, I'm just highlighting over this 95th quantile, and it's interesting that the Southeast and Northwest is like higher weighting pattern. Another interesting fact is for fall, we see like for the lower quantile, there's almost no change over this Northern Great Plain or Midwest, like mostly like Central US, and eventually it gets to the weighting pattern if we go to the higher quantiles. For winter, it's interesting if we see that the winter and spring kind of has a similar spatial pattern in terms of Northeast and Southeast part. We see more higher, like more intense, or like more weighting pattern in winter over this area. So these were basically trends, and then we need to normalize it because this is coming from SSP 370. So how I normalize it, I have all the pixels within the within each region, and you can see that here. And I normalized it from that historical or like climatological percent plan. So in general, this has been narrowed down to two different quantiles. I'm just showing here for median and the extreme or the 95th. If you look at different seasons, I will be explaining only summer and winter here. For summer, the southern Great Plains and or southwest part and some parts of northwest, we see like higher values of like a normalized average change, and that actually has a similar kind of pattern also in the higher quantile. But what are the error bars? So this represents the standard deviation within this change, within this individual region. So that's basically the error bars. Even though we see a higher normalized change, the standard deviation is also higher in those regions during summer. For winter, if we look at the Northeast and Midwest for the 50th quantile and the same for 95th quantile, we see higher average change. And I think in the previous slide, I also explained that in the winter and spring, we see more precipitation, like weighting pattern in that part. And we also see that after normalizing, we also see kind of a similar pattern here at regional scale. So this is coming from just detecting uncertainty because we have large ensembles, like 70 ensemble members. So we're thinking that, okay, 70 ensemble members, like 70 different models. So, and see how their agreeing with each other. So there are like two conditions to meet for each pixel. It's like we have to find out that it's statistically significant, and for that case, we just pick that 0.05 alpha level, and we have to find out for a pixel how many of this ensemble members are agreeing with each other. So it has to be at least like, for our case, we set this threshold is like around more than 50%. So for a pixel, if we see that the pixel is already statistically significant and more than 50 ensemble members agreeing on that, we take that pixel as statistically significant. So I'm just giving one example. This is like seasonal total precipitation. What we found from this analysis is like, for two different changes, like no change agreement, that means there is no change and they do not agree, is like mostly over most regions. We found that for the seasonal total precipitation, except some parts in southern Midwest and northern Great Plains spring, and all regions in fall. That's kind of like some of the highlights from the analysis. And there was like a positive change agreement for most part in Northeast, Southeast, and northern Great Plains in winter. I've done the same thing for daily maximum precipitation. There's another index I also use for this analysis, that's like intensity-based index, so the intensity of wet days precipitation. So this is for the daily maximum. So before I just showed this seasonal total, this is for the daily maximum. Regional scale change. I'm just only covering the summer and winter. So interestingly, we see the same kind of change, like a normalized average change over the southern part, that also governs both 850 like median and 95 quantile. And same for mostly like the southeast to northeast and midwest over winter, and that's also have the, like, this is basically kind of a similar change that we have seen from the seasonal total precipitation. So to narrow down, or like what did we learn from this study? So there are kind of like three types of question I was planning. One is basically how will seasonal precipitation vary across quantas in the 21st century. So in general, we see that like daily maximum precipitation projects of weather are extreme over this area. But to highlight few of those regions is like northeastern region in spring and winter, and drying in Midwest in summer, something like that, and southern Great Plains in southwest in summer. However, we have seen that there are like large kind of like standard deviation within this region of change. In general, another question is like, which quantities are more likely to drive this future precipitation change? We found that the scientific quantity, we have seen that in northeast southwest, this has been governing in spring and winter. And if we have to look at this regional scale precipitation change likely to occur, and that's coming from combining not only the trends, also the uncertainty detection using this Manhandle test, like whether they agree on a change or not. So we have seen that significant positive winter trends in east part of the domain, and also in spring in Midwest. So there are like many more results from other extreme I've looked at, but I'm just showing a few of them. You're welcome to explore more if you're interested in. So now I'll be shifting to a very different region. So here I'm trying to answer, because this area is kind of governed by two different weather systems, like Indian summer monsoon and also like westerlies. So basically, it's very interesting to look at the precipitation of this area. This area has a very heterogeneous and diverse climate over this area. So one question is, do seasonal patterns and elevation gradients and precipitation gradient characteristics signal at finer resolution? So I will explain this why I mean by finer resolution in my later slide. So I have used a new data sets, a newly developed data sets that's called an ensemble product, based on the consensus of the existing products coming from multi-sources. Another one is I also looked at the projected change of extremes using two different scenarios, SSP 24.5 and SSP 5.5 over this area. And this is basically a village in Nepal I visited this year. I just wanted to put that on slide. So this area is basically, you can see this is the elevation profile. of high mountain Asia. It's actually bigger than that. I'm just looking at this from 75th to 95th, and you see the latitude. So to begin with, there is no consensus that one single product performs better to look at trends over this area. So there has been like many research over this area at different basin or scale precipitations to see which product was the best. But unfortunately, there is no product that's kind of the best product. So we looked into different types of products, and I evaluated over from 2001 to 2008. So I've used Eurofile, Chorks, and iMerge. So you can see like analysis to satellite products. They are all related to a common spatial resolution like 5 kilometer. One thing is basically what we did, we just did the average, like the EM is like the ensemble average. That's something, and another thing is like basically is explained here in this paper. What we did here, we took this ensemble mean and we reran this ensemble mean for each pixel from the distribution of these three products. That's a new kind of ensemble, and I'm using this LPM to answer to answer the precipitation change in the historical part from 1990 to 2018 at 5 kilometer at daily scale. So that's what I mean by the final resolution. So I wanted to see how this LPM is behaving in terms of this resolution, and submitted this work, and it's under review. But we have a prequel of this paper is coming, like basically developing of this product. Another one is using for looking at this projected precipitation change using this SPEAR data. That's the CFDL data, but they have 50 kilometer original resolution. Thanks to my like the NASA High Mountain Asia team, I'm a part of this project. So they did some statistical downscaling of SPEAR data and for two different scenarios, and now the output is like a 5 kilometer scale. So I'm looking at these two different products to understand the precipitation change over the High Mountain Asia. So just to give an idea about the annual average from the historical perspective, we are looking at, so this is coming from LPM, the newly developed product. This annual average, only the statistically significant trends are shown here. The upward actually showing the upward markers represents the increasing, and downward represents the decreasing trends. So if you look at, we see this is actually Pakistan, this is India, this is Nepal. We see mostly like central part of India, northwest, some eastern part of Pakistan is kind of increasing. So mostly like the lowland areas of Nepal is kind of increasing, but not all of them are statistically significant. However, the decreasing pattern in annual precipitation are more like kind of clustered in northwest and southeast part of the domain. Looking at the seasonal patterns, the left graph is basically summer, going from June to September, and the right one is the winter, going from December to February. And the same, so if we look at the precipitation change here for this period from 1990 to 2018, we see mostly the same area. We have seen these annual precipitation increase, the same areas are increasing in summer, but actually most of them are not statistically significant. Whereas we see more decreasing pattern, and they are statistically significant at 0.1 significance level over this area in summer, mostly located or clustered in the northwest and the southeast part of the domain. If we look at the winter precipitation, it's interesting. There is kind of a gradient of decreasing pattern, and we see mostly like decreasing part of winter precipitation over Tibetan Plateau. So this is a basin that's called Tarim Basin. There is almost no change in precipitation in winter.
So can I ask a maybe a naive question? Just with these, you can see the grid, right? So there's some grid imprinting at least. So is this because of the mismatch of the resolution of the data sets that you're using from the observations, then doing the change in the future, or why is it so? Like, why can I see the grid? I mean, I guess it's a little.
Oh, the question is like, so this is coming from this LPM.
Yeah. So, okay, but why is it? I mean, this is what if this was a numerical model, I would question it right away that you have grid imprinting, and I know it's not because it's this different product, but I'm curious of why it has, even in the areas of dry. I mean, it's just I'm a little confused by that. We can maybe talk about it at lunch, but
So I think if I understand this, but this is like, so the density of this, if we're looking at this Manhattan test intensity, you can change this intensity or
okay.
to look at this it's like.
So, but even if you go back on the previous slide, this is just the annual average.
Yeah.
And I would say that it's a little worrisome that it's checkerboard. You can see some of this. It's going from white to brown to white grid box next to each other. So to me, it seems almost like there's a mismatch of resolutions or something between something interesting going on. We could talk about it at lunch. Right?
Sure. So yeah, these are like 5-kilometer resolution. So. Okay, so then I looked into this projected precipitation using the sphere product. So this is a very busy graph because there are like a lot of products here. So I'm sure you can see that there's a this dashed line represents the LPM, and this is basically looking at the change of top 1% precipitation. It's a fraction because the change to the total precipitation, how the top 1% is increasing or decreasing, or there is no change at all. So this LPM was the reference product because LPM was used to bias correct this sphere data set. So that's why I put it here. This orange line, this dashed orange line is the ensemble, this 30 ensemble members coming from sphere. So this is the ensemble average, and this shaded region is like the spread of the ensemble. So you can see that mostly that shaded region can encapsulate this LPM, but sometimes there are like few exceptions there. Then again, I don't think it can be seen from here, but there was a gray shaded region in that represents SSP 58.5, and the blue shaded region actually SSP 24.5, and the dashed lines are the ensemble average from these 30 ensemble members. We see almost a similar kind of change is the top 1% precipitation until 2060, and after that it's kind of like that they're like diverges, but they diverge, but they actually also have a upward trend in and top 1% precipitation. So some of the results to highlight here is are like we've seen that there are like increasing average trends over mostly the lower elevation. So the lower elevation of the southern Nepalese border or Indian subcontinent. There are some fewer statistically significant regions in terms of summer trends. So mostly are like kind of localized trends. And there is a shift in heavier daily precipitation that's kind of driven by this SSP 58.5. And so in general, like we can conclude that the local physiographic conditions account for different rainfall patterns. So this is a very different approach. So up until now, I was explaining more about long-term change or long-term like of extremes or average precipitation. But this is kind of like case study where we looked at the extent of or the severity of a flood event and try to understand the extreme rainfall that occurred. So just few of the statistics are kind of like they're like it was a very bad event because like they're like the death toll crosses more than 1,400 and 33 million people were affected in terms of casualties, and 1/3 of the country, like the fact I'm talking about Pakistan, was kind of under the flood. So and the national August precipitation was above 200%, like 200%. And there are like two areas I'm more interested to look into. One is like the southern Balochistan and Sindh is like you can see it's like higher than 500, 700% in general. And so some of the studies I've looked at into the drivers, what caused this type of extremes is like the extreme monsoon rainfall with melting glaciers from the northern part. There was a heat wave during May that might be kind of the causes, and also the moisture supply from Arabian Ocean. So for this study, I looked into the Almosh product, that's a satellite product. For this type of analysis, sometimes if we're waiting for a model analysis product or something like other products, It's very difficult to find sometimes, but satellite products is kind of like the easiest option to look at. So I looked into the precipitation statistics, mostly like multi-day precipitation for the summer, mostly like from June to August. That was kind of the idea because the storms or the extremes were kind of concentrated during August time frame. And I also looked at another index, that's standard precipitation index. It's kind of like the deviation from, it actually shows that the deviation or the change from the normal precipitation. So, and it goes from n windows. So for my case, I was looking at 5 days window and the 30 days window. So it's basically for 5 days, I'm looking at earlier 4 days and the day calendar day. And for 30 days, I'm looking at the earlier 29th days and the calendar day. But I'm only showing here only the 5 days. So the study domain is basically the southern part, you can see here. So I just cropped it here. So just to give an idea of what would be like the multi-day precipitation here in case with the maximum 5 days precipitation, and these are standardized based on the climatology from 2000 to 2022, and we see that above the 2022 precipitation, maximum 5 days precipitation was above normal, something like that, and the quick analysis using this SPI. This is the 5 days window. So I'm just showing for August. So for example, for August 4, this would be like 4 days earlier precipitation anomaly at the deviation and also the August 4. So basically what I'm showing here. So these are the distribution plot from 2000 to 2022. 2021. This is basically the climatological distribution. The dark shade region is same distribution, but this is 25th to 75th. The lighter shades are from 10 to 90th percentile for only August. And there is like SPI value for 2022 only for August is basically shown in the blue color, blue line you can see. And for another kind of this extremes flood event, this extent flood even happened back in 2010 over Pakistan. So I wanted to have a reference of what was this 5 days window period for that type of event. So that's shown in the orange color. So in general, if you look at the August SPI values, we see mostly the blue part are within this shaded regions, mostly within this climatological distributions. But after August 16, they kind of like it rises and goes to a very positive, like a deviation or like anomalies, and stays up pretty kind of in that region for at least the end of the month, and then goes back to the distribution within the distribution range. But however, it never reaches to negative part of SPI. But if we look at the SPI 2010, it was not like that. So SPI 2010 is mostly stayed within the distribution. So might be the case that this event didn't actually impacted the southern part. It might be impacted the other parts of the region. So just to combine everything, what I have been doing during my dissertation, during my thesis, is just to use different bunch of data sets to look at different types of extreme indices to understand these hydroclimatic extremes over different parts of the world. So it's better to because these are essential for climate adaptation, mitigation, and resilience mostly. And so this is kind of like 2 examples I just put here. Like this is the climate vulnerability index coming from not only so these are coming from demographic and ecological models, which is just to show that some of the areas are more vulnerable than the other areas. So it would be really important to study these areas. And one thing is, in terms of the NASA HYMET project, which I was part of, they also looked at other landslides. So because those kind of extreme indices is kind of are useful to understand the landslides, because some of the extreme rainfall cause those kind of landslides over this part. So So understanding extremes is important. Um, so finally, this is basically what I am up to now. Kind of will be working, and I'm kind of working now. Is like to understand the climate change impact on extreme weather events. So up until now, what I've done, all of it looking at trends or different types of patterns, but this is more like understanding a particular weather event. So now I'm looking more into this, understanding the or quantify the intensity of short duration rainfall from extreme weather events, for example, the hurricane. So particularly, I'm now looking at it's a Hurricane Ida that was kind of really intense over the New Jersey and the northeast part. So I'm trying to understand the impacts of warming signals on storm remnants. This is a part of the Hyperfacet project. Just to give an idea of the type of work that just started to look into. So this is the rainfall events, like basically the remnants from the Hurricane Ida. This is the maximum hourly precipitation. And I'm just looking at from 20 that have this even occurred in 2021. And I'm looking into just the even dates, basically September 1 to September 2nd. This is from 8 p.m. to 8 a.m. And this you can see the intense maximum daily rainfall precipitation over northern New Jersey and over the northeast part. This is the scale of millimeter scale. You can see that how extreme the remnants of Hurricane Ida was. And if we would like to accumulate this precipitation over like n number of hours, for my case, I just put it like 6 to 8, 9 hours, for example. You can see the accumulated precipitation in millimeter scale and how intense that was, and it stands out if we compare the other areas over this northeast part. So this is something I'm looking into, and now actually moving forward, I'll be looking more into the frequency analysis of this type of event and how rare or severe this event will be in future, in term as as a function of thermodynamic change. So that's all. So there'll be like more results coming from this project, basically. So thank you so much for listening. I think that's all from my part. I'd love to take any question.
Okay, so we have some time for some questions. Yeah, Kamazima?
I've got two questions. The first one is along what Kevin had asked before, with having all those checkmarks around. Is it because of the LPM method? Because I see you replace the neighborhood value with the sorted value, so you are introducing, I'm gonna call it noise because I don't quite understand it.
So yeah, so thank you for that question. So it's in the paper they mentioned when they were re-ranking the values of a precipitation field, there is a radius, so that's kind of 25-kilometer radius, and they also save that information. So it's not just like they're replacing it from precipitation from Virginia to California. It's within a radius of 25-kilometer scale, and they have tested this for other scales like 50-kilometer, but I think 25-kilometer works the best for it. Yeah, so if that answers your question.
Okay, so let's move to the almost last slide about the vulnerabilities index. That's the one I'm interested in.
Oh, this one?
Yes. So on the left panel, I was looking over Saudi Arabia, it's all red, so it's very high vulnerability. And I'm thinking that should be because of lack of vegetation and stuff like that. But then the Sahel region is white. Why?
So this is not my study. I just put it for to have an idea. Okay, what in general what we know from other models, other people have worked on, not only looking at these other models, just also looked at demographic and ecological models. So I'm just like, okay, spotting out what are the vulnerable areas in general, and then why we need to understand the precipitation status. This is just for an example.
I mean, I don't know any, I haven't looked at this, but I would wager a guess, which is either it's a lack of data, or it's that I mean, when in the Middle East and on the peninsula there, that it's the extreme heat values, particularly as you approach really high temperatures, that might be what's driving it, and it might be just like a threshold, and then all of a sudden it makes it. But I don't know, it's an interesting. I mean, you also see it like all in the middle of Australia too, right? Which is so. Yeah, Minghua.
Yeah, so about the first part, you showed the trend in summer, Northern Virginia and Maryland. I am intrigued by this large spatial variability in this small domain. Yeah, that's right. So you see Southern Maryland and Northern Virginia. I'm wondering whether this has anything to do with like the mean distribution of precipitation, whether say there is maximum in that corner, therefore the trend signal is much better.
So I didn't have the map here, but I actually looked at the PDFs of different seasons for example, in earlier decades from for 20 years, for mostly looking at this top change, like say 5% precipitation, and I've seen something like projecting to a higher extremes over this area, but yeah, there's like high variability in summer over this part.
But to maybe add to what Minghua, I mean, but so this isn't a very large area, right? So this would be like, right? It'd be like almost looking at Long Island and seeing half of Long Island has this huge precipitation increase and the other half doesn't. And so I guess, I mean, do you know? You haven't done any level of like a moisture budget analysis or trying to see, is it a change in like a synoptic scale events or anything? Because
the other variables would be interesting too.
Yeah,
E-
or
even if just looking at like the mean distribution of precipitation in this region, whether the topography has a big impact. That's a good point.
That's a great point. It's some of the other studies I looked at. I found like one study that called like maybe the hurricane tracks over the inland was changing some of the results, and also the other studies that looked at like seasonal precipitation over this area. They also pointed that summer precipitation is increasing. So there might be some other things. So this part is like a part of Chesapeake Bay, and actually it's a large area. After that, I haven't included that one. So some like this is kind of like coastal areas or like lowland areas. These are more connected with this extremes in summer. Something like that might happen, but I think I need additional data sets to look into.
Do you plan to look at like Long Island and New York City area after this resolution?
I would love to definitely, if I have the opportunity. I definitely would like to.
Can you just go back one slide? Go on, look at the left part. For the first 15 years, like from 80 to 95, the extremes are less than more recently. See, like after 1995, it's about 6, way off. But some people would call it outliers. You see what I'm saying?
Yeah.
Did you? Not sure whether you talked about that or not.
So the thing is, just to have an idea about the change, I did this linear linear regression, but I guess like most of the data sets are outside this confidence bound. So kind of I don't trust this model. I would apply grid by grid scale to see the changes of the annual scale, and then we see that some of the values are also negative. So that's why this is just like an idea.
I'm not talking about that, but about the line there. Look at the extremes; they're increasing with time, both positive and negative extremes. See, since about 1990, now 80 to 90. Okay, you've got a few. Let's call them outliers, but more recently, They're much
They're on the
more
lower, yeah.
extreme, right? Both above and below. Anyway,
Yeah.
that's a little small, but, what's the future? What have you read about the future of the Ganges River discharge? I mean, what do we expect for them till the end of the century? Have you read about that?
No, I haven't watched it again. Is there mostly like, so this is, so for the high mountain area, I talked about high mountain area.
In India.
Yeah, so I've only looked at precipitation, but didn't have this like correlation of this straight precipitation to stream flow. But I think it just a few minutes.
So maybe I'll ask a quick question, which is, so, today is the first time we saw the sun since Friday. And so I'm curious if in any of your work, if you've looked at not just extremes from like the RX 1 day standpoint, or even the RX 5 day or 7 day, but if you've looked at like consecutive wet days, or metrics like that aren't maybe extreme in terms of the amount of precipitation you got, but extreme in the fact that it rained for consecutive days in a row.
I did that over my modernist. I don't have the map here, but yeah, I think at some point I realized sometimes the consecutive dry days are increasing, but the magnitude of precipitation on wet days are also increasing. So it's interesting to, if we have to combine, okay, so there might be like more dry days in some parts of the world, but when it rains really like extreme. So that's another viewpoint that I did some an analysis over like consecutive dry and wet days.
I'll ask one more question while this slide is up. So, later on in kind of the last project or second to last, in the last project, you were showing that you were using this, this new technique that has, 3 different data sets that are feeding into it. But this analysis here was done with 1 observational data set.
So it's analysis, but it's not like atmospheric analysis. They merge, like they have like CPC data, then they actually integrate the CPC data based on some radar data sets. So in a way, they have also merged different data sets.
Yeah, so I'm just curious though, like if you were to kind of getting at maybe even Minghua and Malcolm's question, right? If you were just to use a different observational data set, or if you were to use, whether it's even using station level data within this region, would you still see the same amount of variability and the same pattern? I mean, of course you'd expect so because it's a reanalysis, but I think at scales this small, I'm not always confident that the reanalysis products will produce the same signal that the stations will actually have. It would be interesting to see if it's consistent across independently driven type of data
I
sets.
did some validation with the GSM data over this area, mostly over the airport data sets, those stations. They match pretty well.
Okay.
Because one interesting fact about NLS data is like it kind of follows the topographic variation over this corners. So that's one of the reasons we chose this data. And it's interesting. And it's like it looks nice because it has like spatial representation. But yeah, I did some validation and we are kind of happy with the results.
Have you ever looked at any of these statistical downscaling techniques like LOCA or MECA or whatever it's called? Okay. It would be interesting to see if they kind of see similar patterns over. Okay, well, maybe, are there any other, I kind of asked a bunch of questions. Yeah, Levi.
I think this is a bigger question. I'm just curious if you, or maybe Kevin, who's also worked on extremes, have delved into the idea of how the sort of longer term climate variability influences extremes. I know we're really limited in terms of how much time the data covers, but I would imagine that the background climate state has a big impact on the extremes. And I don't know, can you say anything to that or to how that influences our future projections?
So I think this is probably more related to the part in which you were using the CESM large ensemble for future projections and doing, because right, just in the sense that here, when you're projecting to the future, not only do you have changes in the the mean state, right? So the thermodynamic signal, you also have a pretty large change in the projected change in ENSO and NAO and stuff like that in these large ensembles. Have you, I think Levi's asking if you've tried to decouple that. Is that what, is that, or?
I'm also just curious if that field is being explored very much. I mean, this is a large ensemble.
Yeah,
I think we probably don't have a whole lot of confidence that that large ensemble is predicting future background climate variability very well in the first place. So the extremes are pretty dependent on that background climate state.
yeah. Well, okay, so that's a broad question. Which you did preface it with that, which maybe we should move it to lunch, but I think that's, I'll just add something real quick, which is, I think that the models are sometimes, okay, if you look over the historical era, it's not that they're bad at interannual variability, like things like that. So if anything, they've actually improved significantly. They'll just have an ENSO event at a different time than actually happened historically, and that's anticipated. But what they will project a change in that type of variability, but the large ensembles have shown that you can have models that produce, even in the same modeling system, you can have a future that has more El Nino-like or a future that's more La Nina-like, for example. I'm just using that as an example. And I think a little bit what Ishrat showed was that in some of their analysis, they focus on not just looking at something statistically significant in change, but seeing if there's a model consensus in the direction of that change. I think you had shown at one point. So that's one way to, I think, get at the question. One of the things I'll just finish, we'll wrap up, which we can talk about at lunch, but one of the other things that Ishrat is starting to look at is a data set that takes the interannual variability part out of it. So it only has the thermodynamic climate change. So it replicates the last 40 years under different features. And that might get at how much of this change is just from the increase in moisture versus how much of this change might be due to changes in things like storm tracks, things like that, which I think start to get at the question you're asking. So we should take it to lunch though. No, I don't want to cut it off, but it's 5 minutes. So as a reminder, we're going to go over to lunch now. And there'll be time at about 1:45 at the latest for students to chat with Ishrat. And so, and I'll just mention one more thing, which is in the future, you should be able to see Ishrat around the halls. She's not here full time yet because she's working on moving to Stony Brook. So you won't see her for maybe a couple months, but you'll know how to contact her if you have any questions via your email. So thank you, everybody. And thank you, Ishrat.
I want to take a photo of one of your slides. Thank you. No.
No,
That's the slides. Okay, got an earlier slide. Keep going.
I'll be back.
Keep going.
Yeah, I was thinking.
Keep going. At the beginning? Oh, then go forward. Sorry.
It's like an hour or so, but I was going to work on a project around 2.
Okay, yeah, I just.
I mean, if you guys are free around in an hour, I'll be there.
And a box on the left-hand side that I wanted to take a picture of.
Yeah, I already downloaded the data. I can just send it. Actually.
This one?
Yeah. Okay, well, yeah.
At the end of that?
Yeah.
I couldn't find it. I'm sorry. Just go back one more time. I thought it was towards the earlier part of the talk. I tried to get my camera out of time. Early in the talk, yeah. Had a whole bunch of numbers on the left.
I think this might be the one.
That's it.
Oh, okay.
That's the one, that box on the lower left is the one I'm going to take the picture of. Good, thank you.